It's my understanding that my grader graded your exams. I have not even remotely looked at it. And there's still a person who has not yet taken it. So as soon as that person takes their exam, then I will distribute them and all that kind of stuff so you can see what happened and all that kind of good stuff. I honestly have not looked at anything, so I don't know what the average score is. If it is lower than I expected, there may be an opportunity to make up some points or something like that, but I'll figure that out probably at some point this afternoon. So today we're going to start talking about three-phase power concepts. Just a moment here. So today isn't going to be a lot of math. It is going to be a lot of background information to figure out what the heck is going on. Okay. So let's call this part right here an introduction to three-phase. And you will usually see me abbreviate three-phase with the following thing, 3 and the letter phi, circuits. So most of us are at least somewhat familiar with the concept of a single phase circuit. Whether or not you guys realize that is another thing entirely. But in a single phase circuit, we have a voltage source. So I'm going to put a little line like this. We're separating the different parts of our system. And I'm going to say that over here we have some voltage VP, where that VP stands for a phase voltage with some particular phase angle, theta V. And then over here on the right-hand side of the screen, we are going to have a load, which I am simply going to designate as a generic load having some impedance ZL. And then connecting, so let's see, this is our source side. This is our load side. And then connecting the source to the load are transmission lines, where in a single phase circuit, we usually have a hot wire and a neutral wire. Right. So this diagram literally describes every outlet in this room. So there is a single phase voltage source. That is the secondary of one of the transformers outside, feeds into this building, and then transmission lines are used to distribute electrical power to these outlets. And then when we plug something in, we are loading said outlet. Okay. So every circuit that you've ever plugged anything into in your home is an example of a single phase circuit. Okay. This middle part right here, just to be clear, is the transmission line section of our single phase power system. We are going to start analyzing three-phase systems. And there are lots of different configurations that we're going to look at. So I'm going to start with something simple just to illustrate why you might use a three-phase system, right? So let's say that we have the following system. we're going to have a voltage source here, where we're going to have some phase voltage, and I'm going to call this theta A. We're going to have another voltage source here, where we're going to have a phase voltage, exact same magnitude of voltage, but the angle is going to be different. So theta B. And then down here, we'll have a third phase voltage with an angle of theta C. And all of this represents our source. Much like with our other diagram, we are also going to have a load, but in this case, we're going to have a three-phase load. So I'm going to call this ZLA. So the load impedance on the A phase. ZLB for our load impedance on the B phase. And ZLC for our load impedance on the C phase. And let's call everything that we see over here our load. And then once again, connecting our source to our load will be transmission lines, where this is our A phase line or wire. Here we have our B phase transmission line. And here we have our C phase line. Okay. So we're going to get into some notation things here in a moment, but I want to talk about why we might use a system like this. So put an arrow here saying that this is a three-phase system. So let's say, just for the sake of argument here, that our phase voltages VP are the same in our single phase system and our three-phase system, right? So in our single phase system, we have voltage source VP that is supplying power to some load ZL, right? And it takes two wires to do it. We have a hot wire and a neutral wire, okay? So there's some fixed amount of power that's being supplied, and it's taking two wires to transmit that power from the source to the load. In our three-phase system, we have three phase voltages and three loads. So with all things being equal, our three-phase system is going to deliver 3 times as much power. Anybody have a problem with that statement? How many wires do we need to connect our three-phase source to our three-phase load? 3. So that means we're able to deliver 3 times as much power using only 1.5 times as many wires. That is significantly cheaper to the electric utility. When you're talking about running transmission lines for hundreds of miles and things like that, the least or the smaller amount of copper that you can use to get your power from point A to point B means that the system is more economical. So that's one of the biggest reasons that three-phase is the standard method of electricity distribution in really every industrialized country. Okay, three-phase power is used largely because it's significantly cheaper to distribute power using a three-phase system. Okay. Now, there is another reason that three-phase systems are used that we're going to talk about a whole heck of a lot in your electric machinery class, which you'll take next year. We're going to touch on it here very briefly, but in a three-phase system, the average power developed by a three-phase system and the instantaneous power developed by a three-phase system, which we didn't really talk about instantaneous power before, they are the same thing. It's a constant quantity, right? So let me explain what I mean by that. If we have a single phase system, like the outlets here in this room, and we supply power to some type of load, the voltages and currents are sinusoidally oscillating. And so when we multiply those two, that sinusoidally oscillating voltage and that sinusoidally oscillating current, what do we get? We get a DC component with a sinusoidal oscillation superimposed on top of it, which means the power is sinusoidally oscillating as well. So the power that anything that you plug into a receptacle in your home or any one of these type of receptacles, the amount of power that it's receiving isn't a constant value. It is going up and down around some DC operating point, and that DC operating point is the average power. Three-phase systems are designed such that all of the oscillations are exactly 120 degrees out of phase with each other. And when you add them all together, it appears to be constant. So if you're able to deliver a constant amount of power to something like an electric motor, what do you think that means? So what do you think would happen if you tried to power an electric motor with power that was changing constantly? The speed of the motor is going to change constantly. The torque being developed by the motor is going to change constantly. So effectively, your motor is going to vibrate, and those vibrations are going to decrease the lifetime of that motor. Well, in a three-phase system, if you're able to deliver constant power, even using sinusoidally excited circuits, your torque is constant, your speed is constant, your vibrations are at a minimum, and the equipment will last a really long time. And by a really long time, I mean a really long time. We have three-phase motors across the street in Nethkin Hall that predate World War II that we still use to teach you guys, because it's damn near impossible to break the things as long as they're connected to three-phase power. Okay. So that is the principal reason that three-phase power is used in industrial settings, is because it provides a constant instantaneous power, and therefore all of the motors that are connected to it have constant speed, constant torque, and behave very, very well. All right, so this is one simple three-phase connection. We're going to be discussing the 4 different types of three-phase connections later today, but I want to introduce some nomenclature things here, okay? So on the source side of the system, what I am going to do is I'm going to denote my terminals with lowercase letters. So the terminal of my three-phase voltage source for the A phase is going to receive a lowercase a. The terminal for my three-phase source for the B phase is going to have a lowercase b. And the terminal for my C phase is going to have a lowercase c. This particular source is commonly called a Y-connected source, and we'll talk about that more in a little bit. And so this common point of interconnection is where our neutral wire would be connected. So I'm going to designate that terminal with a lowercase n. On our load side, we are going to do effectively the exact same thing, except we're going to use capital letters. So my A phase terminal for my three-phase load is going to be capital A. My B phase terminal for my load is going to be capital B. My C phase terminal for my load is going to be capital C. And my neutral conductor terminal for my three-phase load is going to be capital N. So having all of these different terminals labeled like this allows us to use a double subscript notation for voltages and currents. Okay. So what I mean by that is I could call this voltage V lowercase a lowercase n. Okay. Where the first subscript denotes the positive polarity terminal of the voltage, and the second subscript denotes the negative polarity terminal of the voltage, right? So if I tell you that the voltage VAN is 120 volts RMS, angle 0 degrees, you know that there is a 120 volt drop between the A phase terminal of the source and the neutral terminal of the source, right? Similarly, we could express the voltage drop across this particular part of our three-phase impedance as V capital A, capital N, where the positive polarity terminal, once again, is associated with capital A, and the negative polarity terminal is associated with capital N. So for voltages, the first letter of the subscript is the positive polarity terminal. The second letter of the subscript is the negative polarity terminal. But we can also use it for currents, right? So if I have some current flowing through the A phase of my transmission line, I could write this current as I lowercase a capital A, because my current is flowing from the lowercase a terminal to the uppercase a terminal. So having I lowercase a capital A tells me the direction that the current is flowing. All right. So we're going to use these double subscript notations to define really every single voltage and current in a three-phase system. All right, so any questions thus far about maybe the differences between single-phase systems and three-phase systems, how we're labeling these voltages and currents, anything like that? Okay. One of the hardest parts about this concept of three-phase circuits and three-phase power is literally the jargon and the language that goes along with it. All of the math and stuff is literally the exact same thing that you guys were doing before this test. It's just complex multiplication of voltages and currents, nothing remotely different. The confusing part is the language. So if something isn't clicking or you're like, I'm not sure about that, please, please, please ask, okay? Because that is legitimately the hardest part of this material. Okay, so once again, any questions so far? All right. So the next thing that I want to talk about is three-phase voltage generation. And you're going to have to bear with me and my inability to draw a pretty picture. I'll try to make this as clear as I possibly can. So I'm about to attempt to draw a very simplified representation of a three-phase synchronous generator. And I know that most of you don't know what half that means, but that's okay. We'll get through it. All right. So a generator is simply a machine that converts mechanical energy into electrical energy. So for a three-phase generator, we're going to have something like this. So I'm going to have this circular outside thing here. And this is commonly called the stator of the system. It's the stator because it is stationary. It does not move. Okay. On my stator, I am going to have windings. And I'm going to represent these windings with these little boxes. And these windings literally represent coil of wire. Okay. I'm going to put a black dot in this one and a little label A. I'm going to put a gray dot in this one and the label A prime. So this represents effectively the send and return windings of our A phase, okay? And I've oriented them along the vertical axis, right? So one is 180 degrees physically located away from the other one. So we have a three-phase system, so we're going to need two more pairs of windings. And we are going to locate them 120 degrees away from each other. So 120 degrees is about here. So that's going to be another winding, and then directly across, I'm going to have its return path. So for this B phase, I'm going to put a blue dot. And for the B prime phase, I'm going to put a gray dot. And the reason I'm using gray on this one is because I'm going to wind up connecting all of the prime windings together in a moment. 120 degrees out of phase with the B. We're going to have our C winding like so. And I'm going to put a red dot here, gray dot here, and label these C and C prime respectively. All right. Now we're going to wire up our stator. So here's the A terminal. Down here is our B terminal. Here is our C terminal. I'm going to wire all of my primes together. And where all of these primes are tied together is my neutral terminal. So this is how our stator is connected. And I'm going to vastly oversimplify our rotor here. So this dot right here in the center of our stator is going to represent a pivot point. Okay. And so what we're going to have is effectively a magnet. We'll call this the north pole of our magnet, this the south pole of our magnet. And we are going to say that our magnet is going to spin in a counterclockwise direction, so that the north pole of the magnet hits A first, and then B, and then C, over and over and over again as it spins. I do not going to update my computer right now. So, have you guys had your class on dealing with electric and magnetic fields yet? Sounds like no. Okay. Well, you're just going to have to take what I'm about to say on faith then. So if you have a magnetic field passing through a coil of wire, when that magnetic field changes, a voltage is induced in the coil. Okay, that is what's called Faraday's law of induction, right? So as this magnet spins, the flux that's seen by each of these coils of wire, represented by the A, B, and C phases, is changing. So we're going to have voltages induced on the A, B, and C phases of our system, right? So as this thing spins, we are going to get some voltage VAN as a function of time. So between the A conductor and the neutral conductor, we'll have a voltage. Between the B phase conductor and the neutral conductor, we'll have a voltage. So let's call this VBN as a function of time. And between the C phase conductor and the neutral conductor, we'll have a voltage VCN as a function of time. Okay. So I'm going to draw a plot here, and it's going to be crappy because I can't draw for shit, but I'll try to make it make sense. All right, so this is going to be time. So I'm going to draw VAN in black. Okay. So let's just say that it's going to start here. It's going to look something like that. VBN is going to be literally the exact same shape, but because our magnet has to turn 120 degrees to reach B, that means that our voltage VBN is going to lag VAN by 120 degrees. So the exact same thing is happening, but it's happening later in time. Okay. So that's going to mean it's going to hit its peak about right there. Something like this. And then I'm going to do, oops, I should have done this one in blue because that's the color that I used. My apologies. Let me do this real quick. Sorry about screwing up the color. Something like that. And then finally, our C phase going to be the same thing, but it's going to be a further 120 degrees out of phase. So it's going to hit its peak there. Something like this. So we have these three voltages going, and they are all 120 degrees out of phase. All right. So mathematically, draw it down here. We're going to have VAN as a function of time is going to be whatever our phase voltage is, VPA, so it's magnitude, cosine omega t, where that omega is set by how fast we're spinning the rotor. We're going to have VBN as a function of time. It's going to be VPB cosine omega t minus 120 degrees. And then we're going to have VCN is equal to VPC cosine omega t minus 240 degrees. So the reason why there is 120 degrees of phase separation between these voltage signals is because there is physically 120 degrees of separation between each coil in the system, okay? So there is a physical analog to the reason why there is effectively a time delay on these signals and why they're 120 degrees out of phase, right? So let's talk about this VPA, VPB, and VPC thing here, okay? So ideally, these would all be the exact same voltages so that we would have identical voltages just shifted by 120 degrees on each phase. So how can we make these voltages identical? Well, if our coils all have the same number of turns, then the voltage that's induced is going to be the same, okay? So these three-phase generators are literally built by robots, very, very smart robots, to make sure that the windings on each phase is as close as humanly possible, or close as robotically possible, to the other windings, so that all of the voltages are exactly identical. Okay. So we don't really look at things in the time domain much because the math is really difficult. So from here, we can express each of these induced voltages in the RMS phasor domain as VAN is going to be our phase voltage, and this is going to be an RMS value, so I'm just going to put a subscript RMS here with an angle of 0 degrees. VBN would be our phase voltage's RMS value with an angle of negative 120 degrees. And VCN would be our RMS phase voltage with an angle of negative 240 degrees. All right. So one other thing to talk about very briefly here is the concept of phase sequences. Okay. So this description represents what's called a positive or ABC phase sequence. All this means is that as the rotor magnet spins, it hits A first, and then B second, and then C third, and goes back to A. over and over and over again. So counterclockwise rotation is a positive phase sequence. There's also a negative phase sequence called CBA phase sequence, where it goes from C, then to B, then to A, which simply corresponds to clockwise rotation. So in this class, we are only going to bother with positive phase sequence systems. The analysis is exactly the same. Literally, the only difference between a positive phase sequence system and a negative phase sequence system is if you happen to have a motor, it would spin in the opposite direction. That's it. So if you ever needed to change the direction of spin on your motor, which some of you might need a motor to spin the opposite direction, you would literally just switch two of your phase windings, and then it spins in the opposite direction now. That's it. And when you guys get into your lab for your electric machinery class, you will see that changing the direction of motor is literally that easy. Just swap a single pair of the connections and it'll spin in the other direction. All right, so any questions about three-phase voltage generation? Okay. We have a generator, which is used. We provide mechanical energy to spin this magnet in the middle, and the spinning of that magnet induces voltages in the stator. Those voltages are going to be 120 degrees out of phase with each other because the windings are 120 degrees out of phase with each other. In this positive phase sequence system, the B phase lags the A phase by 120 degrees, and the C phase lags the B phase by 120 degrees. All of our voltages are exactly the same, except they are shifted 120 degrees away from each other. Okay. So, any questions? All right. So now let's talk about source and load configurations. So we are going to start with the Y connected source. So I'm going to draw this first the conventional way, which I absolutely hate, mainly because it's a pain in the ass to draw, if I'm being honest. And then I'm going to show you how to represent a Y connected source in a way that's a little bit easier, at least for my brain to understand. So I'm going to have this central point right here. That is going to be my neutral connection. Let's call this voltage VAN, this voltage VBN, this voltage VCN, and let's just wire up a simple set of terminals here. So this is going to be our B terminal. Up here is going to be our A terminal. Down here will be our C terminal. And we will also have access to some neutral terminal. Okay. And this neutral terminal is actually optional. Or let me rephrase that. The neutral terminal will be there, but you don't necessarily have to connect a wire to it. You don't necessarily need to use what's called the neutral conductor. Okay. So this is the classical representation of a Y-connected source, and I don't much care for it. So let me show you how I prefer to draw them. And technically, I already have shown you because it's how I drew it earlier. Here will be VAN, A. Here will be VBN. Here will be VCN. And there's my neutral. So these two things are literally identical, but I find the right-hand representation much easier to draw. So that's how I'm going to draw all of the system, okay? So we have a voltage source connected between the A terminal and the neutral terminal, a voltage source connected between the B terminal and the neutral terminal, and a voltage source connected between the C terminal and the neutral terminal on both sides of the page. So they are literally the same thing, okay? So now we're going to get into jargon here, right? So I'm going to define a phase voltage. Help if I could spell. So phase voltages are, by definition, the voltage drop over one phase of a source or load. Since we're talking about sources right now, our phase voltages will be the voltage drop over one phase of our source. So for our Y-connected sources, our phase voltages are simply the voltages VAN, VBN, and VCN. Now we're going to introduce line voltages. Voltage drops between the transmission line terminals of a source or load. So that's how they're defined. I'm going to represent them on our circuits in green. I don't know that I'm going to be able to cram all of them on here, at least on the left-hand thing, but I'll try. So between the A transmission line terminal and the B transmission line terminal, we are going to have a line voltage of VAB. So that's how I'm going to represent it on the big Y thing. Over here on the right-hand side, that exact same phase voltage, or excuse me, line voltage is here. Okay. So there is a fundamental difference between the concept of a phase voltage and a line voltage, right? A phase voltage is the voltage drop over one phase of the source or load, and a line voltage is measured between the transmission line terminals, okay? Two different things. I want to be really, really clear about that, because when we talk about delta in a moment, it's going to get even more confusing than it is right now, all right? We're also going to have a line voltage BC. That's going to be from B down to C. And we're going to have a line voltage from C to A. So these are our line voltages. Okay? VAB, VBC, VCA. Are we okay with that? Anybody have any questions whatsoever about this stuff? Right? Now we're going to introduce the concept. Actually, before we do that, I want to talk about two other phrases that are commonly used to represent these quantities, okay? So you might hear of a phase to neutral voltage. So a phase to neutral voltage would be a voltage measured from the transmission line terminal to the neutral connection. So what would a phase to neutral voltage be in one of these systems? What? You're not measuring in the opposite direction. You're measuring from the phase to the neutral. Yep, there we go. VAN, VBN, VCN are phase to neutral voltages. Okay. I'm not going to use that phrase a lot. Certain textbooks and YouTube videos and all that kind of stuff will use it. So I just want to make you aware of it. I'm going to simply refer to phase voltages and line voltages, but I want to make you aware of what other people might say and how that relates to what we're talking about. Okay. So a phase to neutral voltage is effectively a phase voltage in a Y system because it's measured from the phase terminal to the neutral terminal. It's literally the exact same thing. And then you might hear of line to line voltages. So that's measured from one transmission line to another transmission line terminal. So it is literally the exact same thing as a line voltage. They're just calling it something different, right? So a line to line voltage might be VAB, VBC, or VCA. Okay. So now let's talk about phase currents. So a phase current is simply the current that's flowing through one phase of a source or load. So I am going to define my phase currents as flowing into the positive polarity terminals. So let's see. Let's use this light bluish color. So this is going to be my phase current IAN. This is going to be my phase current IBN. And this is going to be my phase current ICN on my left-hand representation. On the right-hand representation, we're going to have these guys, IAN, IBN, and ICN. And lastly, we are going to have line currents. I'm going to give you guys the definition now, but I literally cannot represent my line currents on this diagram because they only exist when there is a transmission line connecting the source to something else. So we're only going to actually see line currents when we have a full system, not just a source or not just load. And a line current is simply current flowing through transmission line. So you'll bear with me a moment after you guys write this down. Let me scroll back way to the beginning. That current IAA is a line current because it represents the current flowing through the transmission line from the source to the load. So if we don't have a transmission line connected, we can't represent our line currents on our diagram. All right, so these are the different types of quantities that we're going to see. This is a Y-connected source. Anybody have any questions about this one before we move on to the next connection? I'm probably boring you guys to tears, beating this to death. The reason for that is I don't want 800 questions of how do I do this problem? You're asking for this quantity. I'm telling you what the quantities are now. So just to be clear. All right. Now let's talk about delta connected sources. So once again, I'm going to draw it in a way that I can't stand and then show you how I prefer to draw it. So we're going to have one voltage source here. One voltage source here. One voltage source here. Let's make our A terminal be up here. Our B terminal be here. And our C terminal here. So that's going to make this VAB, this one VBC, and this one VCA, like so. So that's the conventional way of drawing it. It's a delta connected source because it looks like the Greek letter delta. And then my preferred way to draw it is this guy. So let's call this one A, this one B, and this one C. So here we have the voltage VAB. Here we have the voltage VBC. Here we have the voltage VCA. So phase voltages are defined in literally the exact same way. They are the voltage drop across one phase of our source in this case. So tell me what my phase voltages are. Exactly right. VAB. VBC. And VCA. They're the voltages supplied by each phase of my source. Nothing hard there, okay? Here's where things are going to go a little bit confusing. My line voltages are the voltages measured between my transmission line terminals in a source or a load. So somebody tell me what my line voltages are supposed to be. I'm sorry, what? Oh, they're definite. If I connected a multimeter between the A terminal, I think I used green, and the B terminal of my transmission line system, I would measure a voltage, right? What voltage would that be? VAB. So what do you think the other two phase voltages are going to be? Exactly right. VAB, VBC, and VCA, where this is VBC, and this is VCA. Drawing them on this side, I have VAB, VBC, and VCA. So in a delta connected source, the line voltages and the phase voltages literally represent the exact same quantity. Okay? So in a Y-connected source, they're two entirely different voltages. And in a delta connected source, they're the same damn thing. Now are you starting to understand why this can get confusing? Okay. What would my phase to neutral voltages be for a delta connected source? I'll give you a hint. Do you see a neutral connection anywhere on there? They don't exist. Right? But my line-to-line voltages very much do. So that's why understanding what all this jargon and nomenclature means is so important to figuring out what the hell is going on in one of these three-phase systems. Okay, phase currents. So I want to say I used this little blue line, the blue color. So once again, these are just going to be the currents flowing into the positive polarity terminal. So we're going to have a phase current IAB, a phase current ICA here, and a phase current IBC here. All right, so any questions about our delta connected source? What the phase voltages, line voltages, or phase currents represent. Okay. So this is just another way of connecting a three-phase source. The internal connection on the stator is just slightly different, but otherwise things are the same. There aren't really any hard and fast rules for why you might want to use a Y connected source versus a delta connected source. It's mainly just kind of what generator you buy. All right, so there are only two different types of connections, right? So we only have a Y connection and we only have a delta connection. So we are done talking about our sources. So now let's move on to delta and, Y and delta connected loads. So much like before, we have this central point that is going to be our neutral connection. I'm going to refer all my terminals over to the left-hand side. So this is going to be my B terminal. Up here is going to be my A terminal. Down here will be my C terminal. Here in the middle-ish will be my neutral terminal. So this impedance is the ZYA, so it's the A phase impedance for this Y connected load. This is going to be ZYB. This is going to be ZYC. Drawing it in the way that I prefer. You have ZYA. ZYB. ZYC. There's my neutral terminal. So somebody tell me what my phase voltages are going to be. Yeah, so effectively, all of these quantities are going to be the exact same thing as we saw for our Y connected source, except we're going to use capital letters because now we're referring to a load. So Garrett, I believe you're 100% correct. Our phase voltages are simply VAN, VBN, and VCN, which I can represent on my diagrams like so. Hold on just a second. Why is my computer not charging? Totally says. Says it's plugged in, but it's also driven by 12%. I don't know. The light is on. All right, we're just going to keep going until my battery dies, I guess. So here's VAN. Here's VBN. Here's VCN. On this diagram, a little easier. What about my line voltages? Yep. A to B, B to C, C to A. Again, nothing more than measuring the voltage drops between the transmission line terminals.